Okay, we start up again. Continuing now, looking into unsteady viscous flows. So we sort of make a project out of this unsteadiness for the when we are also dealing with finite differences, and of course trying to solve the Navier-Stokes. So we start out then by writing it for an incompressible fluid, Newton's second law of motion, and we have constant viscosity, Newtonian fluid, no problem there. Here I have written it on the form with a star on all the variables, meaning we have dimensions. So this is with dimension. And as always, I would say, you rewrite your equation system on a non-dimensional form. So then you have to find scales. Of course, this can be a problem in many cases. What is your velocity scale? Sometimes you don't have any, so then you have to invent one. Length scale, that shouldn't be a problem for a real flow. Pressure scale, well, here the dynamical part of the pressure. And then a time scale. Well, that's a big question. Do you have a time scale or not, depending on your problem? If you have one, a time scale, and now just rewrite the equation on this dimensionless form, you get something that is called a Reynolds number, or actually 1 over the Reynolds number, but you also get something in front of the time derivative, something that is called the Strohol number. So I'm going to work a little with this Strohol number. Not that important in practice, it's actually just a time scale, nothing more. And typically what you do normally, you choose a time scale, or you create a time scale, since you have both length and velocity. Okay, then inserting that time scale here, you see the Strohol number just becomes 1. And then Reynolds number is the only parameters left. But sometimes, in some problems, you might have a different time scale than this L over U. Physically, that means either you are imposing some unsteadiness on a flow with a certain frequency, say a paddle moving, a turbine, something. You know the frequency, it's externally given. Or it could be a flow, say around a cylinder, where we know you will have this vortex shedding from each of the side at a certain frequency. That's something that's built into Mother Nature. That's not something that we can control. Then this frequency is sort of built into the problem by Mother Nature. And then definitely, yes, we should use the Strohol number. Problem might be if we don't know the frequency, okay, then we can be in trouble. We'll see more of that later on. So, first example. You have a very, very long pipe, and then we say initially everything is equal to 0, and then time equals 0, you switch on a driving force in the problem. Say you have a pressure difference, gravity, something that is pushing the fluid here to the right. We assume axisymmetric flow. And also we say that the flow is fully developed, meaning we skip the entrance part here. Nothing is changing in the streamwise direction. So we are back to a one-dimensional problem in space. The velocity, only one velocity component in the actual direction, and he varies only with the radial position, but also with time. So we are still left with a partial differential equation here. So now the Navier-Stokes momentum equation is reduced to something like this. This one can again be rewritten a little bit. You can write it also in a non-dimensional form. And you can say that the pressure gradient here now must be some sort of the driving force in this problem, which must be then externally given. So here you just have, say, a constant. Then I want a discrete version of this one. So then I choose what we will call an FTCS scheme, forward in time, central in space. That is sort of the first obvious choice, setting up a finite difference scheme for any problem. So for the time derivative, as the one we had, you use the new velocity here minus the old one divided by delta t. That also means substituting this discrete first order forward scheme here. On the right hand side, everything should be taken from the old time level. Fully explicit scheme. So the derivatives here, you will have a first order derivative and then once more, so it's going to be a second order derivative. It's in the cylindrical coordinates, so you have a lot of these 1 over r and r terms. But we sort of use central space differencing. And then inserting these, if you write this one out, then all of these are taken from time level n, the old time level. So you will end up with a pure explicit scheme. Here, choosing different scales to write it non-dimensional. And here for time scale, I had chosen length squared over viscosity. Now the kinematic viscosity, what's the SI units on that one? Well, that's meters squared per second. So this actually will become a time scale. So it's a time scale for the viscous effects. And if you look at the problem, everything equal to 0, and then all of a sudden you switch on a driving force. So he's beginning to move. So say the first tiny little motion for a cross section will be a very small velocity, fairly constant over the entire cross section, except you have the boundary conditions on the wall, no slip condition. So there you have 0. So it will be close to a singularity, close to the wall. So of course in the further development you're going to get the parabola, but still 0 velocity on the wall. So the effect, you might say, from the walls is spreading in the radial direction. And that's a viscous effect. So here the viscous time scale is might be a better choice than using U over L, for instance. Now, if we choose this viscous time scale, also you see the Struhel number actually becomes 1 over the Reynolds number. So that means we will have 1 over Reynolds number here as well. So that's fairly neat when you then write it without dimensions, multiplying with the Reynolds number, that then will enter into the driving force into the equation. And this one actually can be solved. Here, nice, cute little solution. I mean, everybody can see that this obviously has to be a solution of this one. Fairly easy, isn't it? You should have heard about Bessel functions. So it's a very classic solution by Szymanski before the war, I think. So the J0 and J1s, there are roots for the different Bessel functions. And now let's see, does it work? Demonstration program, MATLAB. So the equation here, it's written in this non-dimensional form. The driving force constant equal to 2. Double derivative with respect to r, and then a single, and then 1 over r as well, due to these polar coordinates. My radius goes from 0 to 1, non-dimensionalized. Initial conditions, everything equal to 0. Boundary conditions, you have the 0 on the wall for all times. And in the center, the r derivative. The velocity gradient should be 0. So I use then a Dirichlet condition on the surface, on the pipe wall, and I use a Neumann condition in the center. Then we have to choose some number of points. I don't use many here, just 11, finding the dr. Then I have something here is called a diffusion number, large D. And more of that later. Delta T. I need some vector for my unknowns. I also need the new velocities, new u. So I have two different vectors. So I'm going to overwrite them as I let the simulation run. And then I'm going to need some Bessel functions here, some solution for it. And here my radius vector. So now the entire program is not bigger than this. That's the entire loop for all time steps. Okay, I have to create the first one there. That is the boundary condition in the center of the pipe. So this one I have to sort of calculate specially. Derivative equal to 0, using the first and the second point. For the internal point, we will have this FTCS scheme for all of them. Forward time, central space. And then when I have calculated all of them, I can update it, and then finding the analytical solution and plot them together and see what happens. So here you have should be an infinite sum of all these Bessel functions. You don't need that many actually. So we can see how this one runs. Take it, remove that one. There we go. So here is my center in the pipe. Here is the wall. 0 velocity here. And at the first time step, yes, everything is started to move, but I still have 0 up here. And then we can step the solution forward in time. Whoops. That was not. Why not? There we go. So you see they follow quite nicely for every time step. It's a little deviation of course, but not too bad. So here one might see the danger. You have a first order method in time. And we are taking quite many time steps here. And it's only a first order method. So the error could be pretty big. The error is of order delta t. And when you take thousands of time steps, might we accumulate the error so that the end result is totally off? But you see, no, it follows quite nicely. We can remove this pause here, and then you can see the animation running faster. So I had chosen the driving force to be 2, and then I know the maximum velocity in the pipe should be 1. So he follows it very, very nicely indeed. And here only with 11 points. So if you want higher accuracy, of course, you just increase the numbers here. Something else. Now this diffusion number. Here I've used it to stabilize the system. If I choose something else here, say 43.43 or something. Then he explodes, unstable. So this is something we need to address, stability, finding a solution. And I think you could push him a little bit, but not too much. So finding these criteria, that's quite vital. There he sort of found it, but he starts to messing around here at the last point. So he didn't really like it. I'll put out these codes for you so you can play around with them yourself. And we are coming back to this one later. Why? What is the stability criteria here? Any questions to this one? That's okay. Yeah, and we don't need these. Yeah, that's a little too much, isn't it? You can't deal with that one today, I think. No. That should be the next topic. What we can do is take a quick look at the projection method. That we can take us time for. I want to solve the Navier-Stokes. Now, I put out on the home page something for you. It's called a compendium, something I wrote many years ago. But you will find there sort of a recipe of how we can break up the Navier-Stokes into a simple program. It's sort of basis behind this Sula algorithm. And here you can then find this projection method, which I'm now going to address. So you have it here already, so you don't have to take notes if you don't want to. So the projection method split time time split, why not? Time split. You have several other names for this method as well, and also you can find it in the book by Fitzsiegert. It's a very easy way how we can find a solution of the Navier-Stokes equation system. The example that we saw turned out to be just one single equation for our unknown, but in general, now I want a solution for the incompressible Navier-Stokes. So Navier-Stokes incompressible, and then I take a tensor notation and just look at the I component of the Navier-Stokes. How do you write that one? Well, you write it like this: du sub I dt. So now we are looking at component number I. So think of it as the x component if you like. So then it will be just u here, okay? And then we have the convective terms. How do we write that one? Then I write uj, and then I take the derivative of ui with respect to xj. You see the trick for this tensor notation? When the same index appears twice in a term, you have to sum them together. So here, this term will now read, if you wrote it out, u du dx plus v du dy plus w du dz. So there you'll have all three terms, the nonlinear terms. On the other side, we will have the pressure derivative with respect to the I direction, of course. Skip the gravity, and then finally viscosity, and then I have the double derivative of ui with respect to all directions. So here again the tensor notation reads dxj dxj. So that's neat. Now I'm going to mix. This is the tensor notation. Now I'm also going to use indexes for the numerical schemes. So here you have to pay attention. Take this term and make it a forward time discretization. I mean, we are going to create forward time central space schemes here in the end, but only take the time derivative. And then rewrite the equation. What do we have? This one now I will write as ui n plus 1 minus ui time level n divided by delta t equals, I throw the convective terms on the other side, so they will then become negative uj dui dxj, the pressure dxi, and then kinematic viscosity, double derivative I dxj dxj. So now only time discretization, no space. So the indexes, they are tensor indexes. Okay? Now, according to this forward time first order Euler time step, everything on the right hand side should be old values. Time level n, the pressure time level n, velocity time level n. There you have an explicit scheme, no problem. You can find the new velocity time level n plus 1 because you know everything, pressure and velocity at time level n. No problem. But this will be wrong, sadly. The reason or the problem is the pressure. We don't have any equation saying time derivative of pressure. How do we update the pressure? That's the pain. So to have this one more correct, the new velocity has to be based on somehow the new pressure. It should be plus 1 there. And that is the pain. This is one equation with two unknowns. That's impossible. We are missing one equation. Okay. Let us skip this part. So if I rewrite this one, I write the right hand side exactly the same except the pressure term. There I now write it as it was first, time level n dxi, and then plus this term. And then I say, okay, I don't have the new pressure, so I use the old one. Then I have to admit I can't find the correct new velocity. I find what's called a tentative velocity field. I find a ui star, and then minus the old one, because I use the old pressure. So the ui star there, the tentative velocity field, very easy to find. That's the explicit version of my equation. Equation 1, equation 2. Then subtract these two equations. Take the equation 1 minus equation 2. What do you get? Well, the time derivative, he will now read something like ui n plus 1 minus ui star divided by delta t. ui n, he will fall. What about on the other side? Well, the convective terms are identical, the viscous terms are identical, so they disappear. But the pressure, he will survive. So here I will have something like minus 1 over density. I will have the xi derivative of, and then the new pressure, Pn plus 1, minus the old one. Still doesn't help. One equation, two unknowns. New pressure and new velocity. I don't have any solution yet. Now we do the trick. Take the divergence of this equation. Take the divergence of the entire equation. The divergence, how did we write that one? Well, you can write it like this. The divergence, that should now read for the velocity, you write it like this, dui dxi. Then that one is equal to du dx plus dv dy plus dw dz. So here I don't use this comma notation, writing this as ui comma I, as I showed you earlier. I use the derivative so we don't get too much confused here. Remember, here it's incompressible flow, so I know this divergence is going to be 0. So taking the divergence of the entire equation, what's going to happen? Well, the divergence of the new velocity, which I don't know, but I do know something about him. He's going to have 0 divergence. So taking the divergence of this equation, he disappears. So what are we left with? I will have a minus and a minus. The delta t, I can keep it here, and rho goes up here, so it should read something like this. Rho divided by delta t. And then here I will have dui star dxi. That is the divergence of this tentative velocity field, the one I created here very easily, fully explicit equation for him. So he's easily found. So here I take the divergence of him, equal, and then on the other side, minus has gone, rho is on the other side, so you will have here double derivative dxi dxi of the pressure difference, Pn plus 1 minus Pn. And this one now you can write on vector notation, nabla square of the pressure equals, and this term here will read rho over delta t multiplied with the divergence of this tentative velocity field, say u star vector or something. There you have it.
Question?
Yep.
Why isn't the divergence of the tentative field 0 as well?
In general, this tentative velocity field will not have zero divergence. It will not be correct because it's based on the old pressure. So in general, no, we can't really tell what the divergence here is going to be. When we have a steady state situation, then the new pressure will equal the old one. Then of course these two guys will be equal. Then it's okay. But for a time developing flow, no. In general, the divergence here will not be 0. Equation 1, equation 2, equation 3. So the algorithm, the projection method, You start by solving, or actually not solving, that's not a good word, because you don't solve anything, you calculate. You start explicit from equation number 2. That one is straightforward, no problem with him. Then we have the tentative velocity field. Next, we have to calculate the right-hand side here as a source term. We have the U star velocity field. We can calculate this divergence. And then we have a Poisson equation for the pressure. I shouldn't write P here, sorry. That was wrong. I think in the notes I used a function, scalar function phi, where phi equals this pressure difference. Here we have to solve the Poisson equation 3 for the new pressure Pn plus 1. And then finally we have to sort of update the new velocity field, and that one is then taken from this equation here. From the equation 1 minus 2. That's the algorithm. So if you know the solution at time level n, you can march your solution forward to time level n plus 1 this way. Fairly straightforward and not involving too heavy math. What's heavy here is the solution for a Poisson equation. This is where you have to work. This is where you pay the price in CPU power. Elliptical equations are costly. And when you have 10 million unknowns, this is going to take a long time. Here we need fast solvers. The first and the last step, that's purely just updating. They don't cost anything. One sweep of the entire domain and you have done the job. No problem there. So the philosophy, yes, you solve an equation system, the momentum equation, but somewhere along the line you have to use continuity. So here we used it in this trick, taking the divergence of this equation. Then we use the continuity for the new time level. So then we got rid of one unknown. That was the trick. Of course we had to use the continuity equation, since at this point we have one equation with two unknown. We need another equation. It's only continuity left. So this is the basis that we are going to continue with, fighting the Navier-Stokes in this way, solving it with the projection method. Any questions to this one?
So the continuity equation is kind of introduced by this divergence equal to 0, or you have to use it?
No, it's here it's given just so that this one disappears from our equation system and we are sort of left with one simple pure Poisson equation only for the new pressure.
So you still have to introduce the continuity?
Yeah, you have to use the continuity. You do the exact same thing actually when we come to finite volume methods, talking about the simple method and simpler method. They do exactly the same as this. Not so easy to see it, but it's there. We're going to address it later. So it's not only finite difference that uses this technique. Now, in the notes that I have given you, I think Also, I used a parameter here, a beta. I multiplied this old pressure term with a beta. So we have a beta here, and here, and here. And then you could choose beta equal to 0, if you like. I mean, this tentative velocity field is going to be wrong anyway. So why not remove this term altogether? Yes, you can do that. And then you will have a little bit simpler Poisson equation only for the pressure, not for the pressure difference. I won't recommend it though, because in a time evolving flow, we are going to operate with quite small time steps anyway. So the difference in pressure is not going to be that big. So you might also say that the previous pressure field is a very good initial guess for the new pressure field. So it's faster to use beta equals 1. So just forget about this beta parameter. You could use him beta equal to 0 if you wanted, but it doesn't help. It doesn't speed up. Okay, continuing then tomorrow at 1:15 in chair 23, I think it was. And then we are going to look at a little bit on the Sola algorithm, and also a little bit further how to solve an elliptic equation system numerically. How can we find a solution here? So we will look into the classical iterative techniques here, Jacobi, Gauss-Seidel, SOR, how to address that one. Because just now, that is what's stopping us. The rest, the first and the second, first and last point here, they are trivial. It's the elliptic equation that's our problem. Okay, any questions from you? Then before you leave, could you please then reorganize the tables